All right. Hello everyone. In this video we're gonna move forward our discussion, and now we're gonna start talking about rate law expressions. So getting the information about the rate law of a reaction is perhaps the most sensitive information. I need to really emphasize that it is the most sensitive information for your reactor design. Sensitive information for reactor design. Okay. If you want to size an ideal reactor, you absolutely need the rate law expression. And if you guys have been following Fogler, you guys will see that from chapter 1 till chapter 5, the book is trying to build up an algorithm in which you have your rate expression, the rate at which your reactants are disappearing, as a function of conversion. So this right here, if I were to give you the highly distilled form of the first 5 chapters, it's the development of the rate law expression in terms of the conversion of your reactant. So this right here is the conversion of your reactant. Okay, conversion of reactant. Very good. But in this video we're gonna start off our discussion by talking about the most simplest form of rate laws. We're gonna talk about, let me scroll down now, we're gonna talk about homogeneous. Okay, we're not dealing with multiple phases right now. We're gonna deal with homogeneous, uniform, nice and well mixed, nice and single phase, homogeneous elementary rate laws. And I'll show you what that means in a second. Elementary rate laws. Okay, good. All right, so let's say I'm gonna give you a very general reaction. A plus B, they react to form C and D. Very symbolic. We're not being specific right now. And let me give it the stoichiometric ratios as well. All right, good. Now, we know that the rate from your general chemistry class, you know that the rate at which A is disappearing is a function of the temperature. Okay, let me use a different color scheme. Okay, so we know that there's going to be a temperature dependence. So our rate constant is going to be a function of temperature. We're going to talk more about that in later videos. And it also depends on the concentration of your reacting species raised to some power n. Actually, hold up. I'm having some decision fatigue here. Sorry about that. N and m. All right. So this right here is a very general form of, this right here is the general rate law expression for a homogeneous irreversible reaction. This is general rate law expression, general rate law for homogeneous, okay, homogeneous irreversible reaction. We haven't discussed reversible reactions yet. That's important. Okay. And now let's talk about N and M for a second. N right here is the order of reaction. With respect to species A, as you guys can see. And M is the order of reaction with respect to, as you guys have probably guessed it, B. All right, so now we know how N is telling you how sensitive your reaction is to your concentration of A, whereas M, on the other hand, is telling you how sensitive your reaction is to concentration of B. Very good. Let me zoom out for a second. Okay. Now, if, and this is a big if, the value of N is equal to your stoichiometric coefficient. All right, so this right here becomes equal to A, and the value of M, the order with respect to B is equal to the stoichiometric ratio of B. Okay, then let me just rewrite the rate expression. The rate expression becomes K, which is a function of T, Ca raised to the power A raised to the power of the stoichiometric coefficient multiplied by B raised to the power of its respective stoichiometric coefficient. This, ladies and gentlemen, becomes a elementary rate law. All right, and I hope you guys are seeing by now what do we mean by elementary rate laws. This right here is the condition. This right here is the condition that's going to give you an elementary rate law expression. Okay, so, and to give you an example of a reaction that follows elementary rate law, we have the reaction of cyanobromide, and it reacts with methylamine to give the following products. Hold on, let me look up my notes real quick. Sorry about that. Oh yeah, it gives you methyl bromide, CH3Br, and this other compound, cyanoamine, I believe. All right, I don't really remember my organic chemistry right now. Sorry about that. And if I were to designate these species as in the following manner, cyanobromide being A, methylamine being B, and the respective products, and I said, yo, let's say the rate at which A is disappearing is proportional to the concentration of A times the concentration of B. And as you can see, these are raised to their orders are 1 and 1 respectively, which is equivalent to their stoichiometric ratios. So this right here, ladies and gentlemen, is an elementary rate law expression. Okay. And I must warn you guys not, and this is very important, not all reactions are going to be elementary. Not all reactions are going to be elementary. This is very important. You need to be very careful. You can't just right off the back assume that the reaction is elementary. That's going to be one of the biggest mistakes you're going to make as a reactor design engineer. So make sure you put some effort into finding the kinetics first. If you don't have kinetics, if you for sure do not have kinetics when you're doing your capstone project, for example, then using a elementary rate law is a good approximation in certain cases. We're going to talk more about those. And I'm just going to refer you to some reading. If your molecularity, I'm not going to talk about that. If your molecularity is equal to or smaller than 2, then it is a good approximation. In some cases, not all. All right, I'm going to link that in the description. I'm going to link some further readings and you guys can do more research on this topic. So just to give you guys a quick recap, we're starting to discuss rate laws, the most sensitive information for reactor design, along with thermodynamics and transport phenomena. I mean, all these three go hand in hand, but this is the most critical for reactor design. Chapter 1 to 5 of H. Scott Fogler, 4th edition, the one that I'm following, is a build-up to give you guys an expression so you guys can formulate expressions for rate laws as a function of conversion. Okay, and now we discussed homogeneous elementary rate laws. This right here was the general rate law expression for homogeneous irreversible reaction. Okay, and in the cases where the respective orders are equal to the stoichiometric ratios right here, then that is the condition for elementary rate laws. If this is followed, if the orders are equal to the stoic coefficients, then yeah, you have an elementary rate law. And I gave you an example of a reaction between cyanobromide and methylamine. Alright guys, and yeah, just to give you guys a fair warning, not all reactions are elementary. That's going to be one of the biggest mistakes you're going to make if some of you assume elementary rate laws when it's not. Okay? Then, so yeah, thank you guys for watching, and I hope this was helpful.